Okay, welcome to our Bucky call for October 4th or 5th, depending on which continent you're on. Just as word to the wise, I'm going to be leaving on October 17th for 14 days into a silent retreat. 14. And so for that 2 weeks, we're going to have to figure out something. Maybe Joe can run the call. He's run them before in the past. He logs in under me and just runs the call, but we'll have to figure out what that is. And I don't know where Joe is right now. And we'll go ahead and begin our call. And Anne, how are you feeling? And what do you anticipate getting out of tonight's call?
Okay, right. I think I'm just happy to be here for the next half an hour, and just to check in and see what I missed actually last week. So that's the reason why I'm here as well, and of course, to spend time with all of you. So Lee, how do you feel, and what would you like to take away today?
Well, I feel a lot better being with all of you. I went through a bout of UTI and it was not good at all. It was very bad. Spent 11 hours and 35 minutes in the hospital. No fun. And I'm still trying to get over it. But I feel great being here with you guys. And I'm anxious to find out what's new. I want to find out more of what's going to be talked about today. Manu, how are you? And what do you look into finding today?
I feel good. I'm present. And I expect a nice and productive ride. Who's left? Fred, how do you feel? What do you expect?
Thank you, Manu. I'm feeling energetic today. Maybe that's magic of my new T-shirt. I don't know. It's a call to the universe. I was wondering what happened to Victor. We had Victor showing up a little bit for some time last week or the week before.
Who is Victor?
Victor from Ivory Coast.
I think that it is too early for him. It's in Ivory Coast at this time. It's 2 o'clock in the morning.
I'm not asking what happened to him. I'm wondering what happened to him. And so it was part of my feeling. And my desired takeaway today is maybe I can learn a little bit something. So that's me for today. So Steve, how are you feeling and what is your desired takeaway today?
I'm feeling pretty good today. Before I leave for my retreat in 2 weeks, I have a lot to do in the next 2 weeks. So when I go into that thing, I don't carry anything in there with me. And and very delighted about these calls and the kind of spark they bring to my life. I'm enjoying the Wednesday call and the weekend call. This weekend call gives a lot of good background. I don't know, you've heard me talk about Donald Hoffman. He's a professor out of Irvine, California, I think, and he likes to talk about consciousness, and he talks about how reality is simply what we perceive to be reality is an interface, like a virtual reality interface, and that somehow human beings can run that interface and can run movies on the interface, and we are the interface. And he talks about how there's a thing called an amplituhedron in the background of everything, that quantum mechanics and physical space breaks down at 10 to the minus 33 millimeters. I think it's millimeters, and below that there seems to be nothing except maybe this amplituhedron, which is a multidimensional kind of polystructure. And he says underneath there's a thing called an ETF hedron. Has anybody ever heard of an ETF hedron? An ETF hedron is a positive geometric shape in the space of Wilson coefficients. Somebody, did you just leave, Lee?
No,
That describes the allowed parameters of a consistent low energy effective field theory derived from fundamental principles like causality and unitarity. The geometry acts as a constraint, forcing the infinite tower of higher dimensional operators within an EFT to lie inside the EFT-hedron, and also implies totally positive structures and linear nonlinear inequalities that any valid EFT expansion must satisfy. In summary, think of an EFT-hedron as a boundary or a safe space for the parameters of Wilson coefficients that describe a low energy theory. If the parameters of an EFT fall outside the geometry, that EFT cannot be a low energy limit of a valid, consistent quantum field theory. Anyway, that's what I've been thinking about for a while. And I haven't made much sense out of it, but I'm very excited to make some sense out of what's going on tonight. I put a text out to Joe, and I'm not sure where Richard is, but I think he said he was going to be traveling. So I guess we're ready to start the call. Is there any other thing anyone would like to say before we're going to begin our reading on one of these pages? I think we're at the truncated. We started with the truncated. We ended with a paragraph on truncated octahedron. I think we're going to start there because it leads into the next section and gives us something to chunk about. But now I've just got to find that book, which I thought I opened. But evidently I clicked on it but didn't watch it settle in. Okay, here we go. It's on page 206 for those of you who are reading along on the book. Okay. Wonderful. About there. Almost there. Buffering in. I'm sorry, I'm not prepared. I apologize. There we go. Wow. Okay, there we go. All righty. And let's share. Just have to find the right buttons. And I have to close that down because I have to reload it. Okay. Boom. So here we are on the page. And I don't think it'll hurt us to start right from here because then we'll go through and it'll set up a context for this. Very interesting. All right, here we go. We can trade off reading, and Anne, I'll be sad to see you go, but so delighted you showed up and shared your granddaughter with us tonight. Very nice. Cool. Okay, truncated octahedron. The truncated octahedron, or the tetrakaidecahedron. Fred, were you able to actually share that in Chinese with your Chinese community?
No.
You took that on as a challenge after our last call.
Yes, but my community is sparse and far between. So I've lived like a monk this week. I've seen nobody, and because it's a Chinese National Day holiday and everybody's away.
Gotcha. A truncated octahedron or a tetrakaidecahedron is also a known space filler. Figure 12.4. That's this guy right here. A model of this semi-regular polyhedron can be constructed by taping together 8 cardboard hexagons and 6 squares of the same edge length. But Fuller is wary of that approach, a geometry which supports the illusion of solids. Instead, synergetics prescribes that we view the system in context. Therefore, to generate this shape, we start with a 3-frequency octahedron, period. With its edges divided into 3 equal segments, this octahedron submits quite naturally to a vertex truncation. As shown in Chapter 9, Figure 9.9, a single frequency 1/2 octahedron can be chopped off from each corner, creating 6 square faces and converting the 3-frequency triangles into equilateral hexagons. So here is your
What does he mean by 3-frequency triangle? Is that something that's earlier in the book?
yeah, 3-frequency triangles. Here's a 3-frequency octahedron.
Yeah, what
And
does it mean?
3-frequency triangles. You know, in our previous things, it goes, in fact, look down here at this. It goes truncating 3V octahedron. And I think that means 3 frequency. And every once in a while I've seen that in the book, but I don't understand it. Mano, do you know what that means?
Yes, I wanted to show you, but my thing collapsed. But you can see this. Can you show? Can you see this?
Yes. Yep.
You remember this guy here? This guy here,
Yeah.
right?
Yeah.
This, okay, no right. This is a 3-frequency here. I'm going to show you how it comes. You see 1, 2, the middle here, these basic triangles. 1 frequency, 2, 3. This is a 2-frequency, this is a 1-frequency octahedron.
Okay.
Tetrahedron. Now look at here. You remember when you divide the original tetrahedron in such a way that you have an implied octahedron?
Yes.
You see these 3 colors? You see the
Yes.
red? You see the
Those are
blue?
the great circles. Yeah.
And you see the green?
Yes. Does everybody see those things? I don't mean to take over the conversation.
That is a 3-frequency octahedron. This one, that is in the middle there.
Okay, Anne, you had your hand up and you're muted. Did you want to ask a question?
No, I'm all good, all good. We can see.
Want to hold it up again, Fred? Manu, do you want to hold it up again so we can?
My thing is collapsing. Right. Okay. Let me just hold it here. This is not.
You're fighting entropy.
Yeah, you're fighting entropy. Very
But
cool.
you can see here, yeah. You see this octahedron. Do you see there?
Yeah.
Yes.
It's multicolored. Do you see the first square? That is
the green.
The green square.
Yeah. Yes.
Do you see the red square?
Everybody see the red square?
Yeah.
Do you see the blue square?
Yes.
That is 3-frequency. This
Okay.
octahedron has been divided by 3 orthogonal planes.
Okay.
That's actually usually the way you present 3D.
Okay.
Right.
Very clear, very sparse yet.
Yeah.
And
so this
concise and efficient.
This and this is the same.
Say again, how is that the same?
Okay, this is the original octahedron, but in an arrangement of closely packed spheres. This guy.
Okay.
This is the stellated of it. Inside here, imagine inside here, you're going around there. That is the stellated part, representation of it. This one is divided. We've divided first the first 4 octahedra here to the first tetrahedra, and then inside we cut again the octahedron in 3 ways, and then it shows you. Okay.
Okay, I have a feeling about it anyway. Any comments or questions from anybody else?
Thank you. Thank you.
Yep.
Thank you very much.
Yep, very clear. The first part of it.
Okay, we're gonna try next time the second part.
Yeah.
Okay.
But everybody can try this, this exactly. We've done this many, many times. This guy. Steve does it all the time. Steve even has one where the octahedron is swallowed by the fourth tetrahedra expanded. You remember that one, Steve?
Yeah, I can. No, I don't
Your paper,
exactly
your,
remember.
your paper model where you can take out the four,
Oh, yeah.
yes. The
And
same
then,
as this.
yeah, it is the same as that. And maybe I'll just show that. No, that isn't it.
Steve has this. This is done with paper.
I have a couple
This,
of different ones back there
yeah.
that
This is
Manu
basically,
helped me build
yeah.
in our
This is
Bucky
two.
calls.
This is two tetrahedra coming orthogonally to each other.
Yeah.
That's exactly what Steve had.
A double tetrahedron has an octahedron in it. It's not implied. A single tetrahedron has the octahedron implied in it. Somehow, when you inside that structure, and when I built this, all the sides are numbered, so I can actually look inside, and that face on that tetrahedron is a 14, and that's inside the tetrahedron. And so I can take this little octahedron and it has a face on it called 14, and it matches right in there.
Exactly.
And so, and it's been real helpful to screw around with this.
It's exactly the same thing as this. Exactly.
Yeah.
And it is. Look at it. When Steve holds it, Steve, hold it the way you held it. Put it inside. Yes. Hold it. Does it not look like this guy?
Yeah, it looks like that guy. Everybody sees that, right? It look except
It's
that
a-
is a three-phase
Yes.
tetrahedron. This is a two-phase
Steve has
tetrahedron.
a two. Yes, it has a two
Frequency.
frequency. I have a 3 frequency here.
Yeah. I have another two frequency. This guy here, it just shows the faces as windows, and it all folds in on itself. So this is the same thing, but it doesn't have the octahedron built into it. It just shows the faces.
Steve, I don't know if you still have the text that I sent you to accompany this. They used to, I've lost it. I built a kind of text to a guide.
And
say,
Manu, if you'll send me a WhatsApp request, I'll make sure that I find it because it's somewhere. It might be on an external drive. I've been having
yes,
some memory issues on my computer, and so I've been having to move stuff around. And that's why, and my computer's so slow because I need to move more stuff off my computer.
yeah,
Yeah.
because it will be very useful because we on it, we say, okay, this is what you need: scissors, papers, and this, and cut them in this kind of proportion in order to put them together and glue that way in such a way that you can obtain this.
Need rock also. Rock,
Yeah.
paper, scissors.
Yes. This is a
Well,
cardboard paper. This was the drawing paper, the A4, the A3 drawing paper that you use. I had, this actually no, this is a folder. What I use here is this. Anybody can get that. You see this folder? You remember this folder?
yeah, they're manila folders.
Yeah. Expand them, then you cut them. You trace and then you cut.
Cool.
That's what I use.
Okay. And what was interesting was this shows, I think this is a dodecahedron, right? And last time we talked about somebody projecting that the microwave background is organized in this shape, which is very interesting. Space filling tetrakaidecahedron by truncating 3-frequency octahedron. truncation of three-frequency octahedron to form tricaidecahedron or a truncated octahedron. The tetrakaidecahedra, truncated octahedra, are space-filling, 4 around each IVM vector. And that, I have a picture somewhere of that background. I used it as one of the cover, as a thumbnail for the recording. By the way, this reminds me, I'm going to sidestep for just a second before we go on, because I want to show you guys something. I mean to do this at each call because maybe it's not helpful, but I spend a little time each week putting together the invitations, and I'm no longer using the Google invitation, and I've realized how dependent I am on it. These are all of the graphics that I sent in last week's. I think this is probably Wednesday's meeting. But each time we do this, I save this, and I save all the graphics that are being shown. Sometimes they're screenshots. Like this is a screenshot from these two down here are screenshots from Fred sharing. I think this is probably another Fred. This is all in podcast. And then these are just things that I found about octaves and things like that. This is from Wednesday's call. And I put these out in the emails that I send every time. And I want to make sure you're all getting the email and you're all getting the invitation. And I had to go back to 2 weeks ago to my Google thing to find the link. So I've got to get a new system for finding the link for this call. Is everybody anybody have any questions about that? Are you getting the emails? Is everything okay?
We're getting the email, but you could also use Microsoft. Oh, Fred, you might not have access to Microsoft, right?
Fred has a
What
Mac.
do you mean? What do you mean, Microsoft? You mean,
Microsoft Meet.
I'm not using Microsoft Meet now.
Okay.
Maya.
Okay, is everybody completely ready to move ahead? I just thought I would share that and make sure you all got it. Okay, how do they fit together? Hexagonal faces of two truncated octahedra come together after rotating 60 degrees with respect to each other, so that square faces alternate rather than landing next to each other and begin to frame a cavity in the exact tetrakaidecahedral shape, which is that 12.4b that we just saw back here. Four tetrakaidecahedra fit together around one IVM matrix. To ascertain the exact relationship of this packing in the IVM will require some investigation. How remote are the vertices involved, and how many cells are incorporated in between? We will answer these questions below, but first we go back to the simpler cases for a sense of the whole progression. Actually, that actually answered some questions for me. Anybody else have any comments? Okay, we'll just continue to move on. I'll read a couple more, then invite somebody else to read if they care to do so. 2-to-1, a review. We can now appreciate Loeb's development of the requirement that a space-filling polyhedron can be broken down into twice as many octahedra as tetrahedra. The cube consists of a one tetrahedron plus 4 half octahedra, or a total of 1/2 octahedra. I'm sorry, 4 1/8 octahedra, or a total of 1/2 octahedron. This ratio of 1 to 1/2 certainly qualifies. 8 quarter tetrahedra, for a total of 2, embrace 1 octahedron to create the rhombic dodecahedron. with this confirmation, we start a list of results displayed in table 12.1. Wow, do I wish we had animated graphics showing all this stuff. The VE consists of 8 tetrahedra and 6 1/2 octahedra, 8:3. Lacking one octahedron, the VE must not be a space filler. A conclusion that is consistent with our earlier observation of the IVM. However, pair a vector equilibrium with the missing octahedron and all space can be filled. So the vector equilibrium is the cube octahedron. And if we pair a cube octahedron with the missing octahedron, all space can be filled. There's a graphic showing that earlier in this chapter or the chapter before. The 2-to-1 ratio also serves as a prescription for complementary pairing. If an IVM system is not a space filler, the ratio tells us what's missing. See, now, evidently, a space filler is some kind of a clue of something, and evidently, the truncated octahedron, that tetrakaidecahedron, is a space filler. And that's the reason why someone would say that that's the shape of the background radiation. I'm just musing. Any other comments or questions or muses or anything?
Hi.
You know,
Okay, I'm first.
yeah. Steve, just now you said that we wish that there is a video, right? So it got me thinking. One of the things that I've not done is actually to look into Amy Edmondson to see if I can find her on YouTube. You know, so I just want to check. This would be Amy Edmondson, right? Can you see that? Is that her?
I'll tell you what I'm going to do. I'm going to do the same thing for everybody, and we'll get on YouTube
Yeah. So anyway, the other thing that came to me, looking at because right now, every time we talk about the tetrahedron and octahedron, we keep chopping off stuff, we keep adding, and then we draw the midpoint and it forms many different shapes within, and it's true whether you make it big or you make it small, or you go sideways, right? So it becomes a universal principle, and I get the idea of the shape of space and so on, right? But what is, I think, fascinating is that every time as part of close packing, right? So you have the tetrahedron, right? And at the same time, we have the octahedron, and then now this tetrakaidecahedron, right? So that those shapes are also part and parcel of if you put together a whole load of tetrahedrons to fill up space, right? So it depends on where you connect the lines, but you will find the shape, and it also shows close packing. So that means that there are many ways to do close packing based out of the tetrahedron. Am I clear? Am I correct in asking this question?
There are many ways to do close packing based on a tetrahedron. Is that what you just said?
Yeah, all the tetrahedrons that, because we've been talking about, tetrahedron will allow us to like pack it very, very neatly and tightly. But at the same time, we've been exploring all the different shapes that comes out from if you were to do a form or you truncate it or you stellate it, or you even draw from the midpoint of the triangles, or even sometimes from the middle of the vertices, right? So, and different shapes will form, and those shapes will carry itself so then that means we can also close pack in those shapes. Is that where?
That sounds really good to me. How about anybody else want to comment? Sounds good to me. I think you have a good grip on it. And Manu has his hand up physically and virtually. And this appears to be Amy Edmondson, and I feel kind of tricked because all this time Richard has been talking about Amy
Yeah.
Edmondson attending a class, and here all of this stuff is about psychological safety.
Oh,
So evidently she's not just a physicist or an engineer, but she's been involved in psychology and sociology, and that's a connection that I did not appreciate until this moment. Thank you for the invitation to check her out on YouTube, and I put that link to this page in the thing. Okay, Manu, go ahead. Go ahead, Anne.
sorry. Yeah, it's okay. Just to finish it off, because linking to Amy Edmondson, I also key in a fuller explanation, but I didn't get much. I got more of these. Yeah, so I don't know how. It'd be pretty cool if we can find her link to the fuller explanation. That would help even further. Right. Anyway, Manu, over to you.
Wow. Did you see that, you guys? There's a great little video that shows hexagons, and
Okay.
then she comes in. How to create psychological safety at work. Oh, that's too far. Let me go back to the beginning of that baby. And it shows a bunch of hexagons, a two-dimensional display of hexagons. There we go. Watch this. There's her. Starts out with hexagons, shows energy moving through space, particles colliding, and then here comes, and the headline is Digital HR Leaders.
Wow.
Very interesting. Well, if Richard were here, he'd be talking incessantly, hopefully. And in the meantime, he's not. Any other comments before we get Manu's hand? Okay, Manu, go for it, dude.
Okay, thank you. First of all, I mean, you know, if Amy were here, she would be very distracted. She's too beautiful. And and I was tempted to chat her. Okay, right. But let's talk about what I wanted to say here. Steve, you talk about 14. You remember?
The 14?
14, when you were putting together the 14 faces.
Well, you knew there were 14 faces. I didn't know there were 14 faces.
Okay, but you say
what's
you
going on
counted
here?
you counted to 14, yes. Did you not?
What?
Did you say he cannot count to 14?
Maybe. Okay. All right.
Yeah, he did. He
Okay.
insulted me one more time. And
Okay,
every
let
time
me-
Manu
let me-
insults me, it just goes
let me
right over
say-
my head. I'm
let me
like a
say-
dumb guy.
Okay. Let me say this is unity from the principle of duality.
Yeah, it's a double tetrahedron. It's unity.
Okay. This unity is made of 1, 2, 3, 4. 1, 2, 3, 4. Does everybody see the 8 tetrahedron?
Yeah, we all see that, right, everybody? Because when you
Does
have
every-
one tetrahedron, you have 4 tetrahedra.
Yeah.
When
It's
you
here.
truncate it. And if you have a double tetrahedron, you're going to have twice as many tetrahedra when you truncate them.
Okay.
And
So-
you'll have an octahedron left over when you do.
Exactly. Now you have the octahedron that is here. That is with this. You still have my red line, my blue, and my green. Red, blue, green. Here. And those are edges of the octahedron. Now, that octahedron, we saw that you can divide it with 3 perpendicular great circles. If you can do that,
Blue, red,
yes.
and green.
Yes. If you can do that, you have the overt and the covert part of unity. The overt part of unity that we see is the 8 tetrahedron. We see stars going, it is tetrahedra 8. But we have also 8 covered parts, which are not regular tetrahedron. They are right angle. They are 60 degrees. They're not at 60 degrees. They are right angle tetrahedron. The eight or the, how you call it?
1/8
Covered part.
octahedron. 1/8 octahedron.
Yes. But the 1/8 is at right angle in part. Is
Right.
like this.
That's what they
Yes,
have to be that way.
Yes. So that it gives you the accounting of the total. Is this can be understood with a simple tetrahedron? Remember that this was obtained from this, or from two like this. So the 1/8 value of the quantum of energy that Bucky talks about is from this. Because we see 8 that are overt, that is seeable, that are outside, that are expanded, that are stellated. We see them. And then the other 8 are inside, are hidden, are in the black hole. So we first have the explanation of a 1/8 value of a quantum of energy, 1/8. The second thing is that we have arrangement of them and the shape of them. That's why Becky says, in order to describe universe, you only needed 2 derivations. 2. Not further. You can do further and do some other things. Like we're saying with the truncated dodecahedron, which is the truncated octahedron, which is also another filling method of space, is a further than 2 derivation of space, and then assembling. But the simplest, and I think sufficient, is this guy here. It allows me to calculate the structure, that is the tetrahedron. It allows me to also resolve the polynomial equation that gives me the phi. The pi, I cannot calculate it. It is given. It is given from transcendency, from outside of our system. Remember the hierarchy of system? Where did I write it this morning? Yes, of unity, system, structure. A system is something that is vectorial. That you can say this is input, that is output. That is the system. Unity is a whole. And the structure is a quantized, is a quantity that you can measure. Then you can go into what Steve usually done, hyperstructure. You go further. But is that necessary for our level? Yes or no? That was the crux of my intervention. That if I can understand Bucky and what he says, using only the tetrahedron and the octahedron, and truncated that octahedron to fill the space, that is enough. And what is good about it is that it can be represented in a way, in a simple way that we can see. I'm through, Steve.
Okay. Fred, did you understand what Manu just said? I'm sorry to put a challenge on you there, Fred. I didn't mean to
You
do
put
that.
me on the spot there without
Yeah.
warning.
Because I'm not sure I understood what he said.
Yeah, but that's usual, no?
Come on. This is a public meeting. This is a
I
public
know.
meeting.
Yes,
You
yes.
say that you are hitting on me.
There, but so everybody can see for themselves and agree with me. The the point is, I understand some of it, and I some of it is not exactly clear. That to the point where I could take it and explain it myself with my own words. That is, my understanding, what I mean by understand, if I understand something, is I can take it and re-explain it to somebody else with my own words.
Yeah.
I understand all the
Okay.
words Manu is saying, but not everything is comprehended by my. Wait a second, let me answer the question, Manu. So some of it, I could take it and re-explain it by myself with my own word. Some of it, I understand all the words he's saying, and I think I understand what he's trying to tell us, but I could not re-explain it by myself with my own words. And
Okay.
the last part of it is I understand all the words, and I have no idea what he's talking about because it's either a new concept for me or this is something that the way he approaches it is different from the way my mind is working. So some of it I don't understand. But that's why I'm
Okay.
here. I'm here because I don't understand what Manu says, and then he says it.
Let me borrow 2 minutes. Can you, Steve, I was drawing this. Can you take
Yeah.
a
Can
snapshot of this?
I'll be glad to take a picture on that, and I would like to comment on what Fred just said. Fred just took the words out of my mouth. If I had the words in my mouth, he would have taken them out. But I agree totally with Fred. Some of the concepts, some of the words I understand. Okay, I've got it, Manu.
Okay.
I'm
If
going to
after
share
your
it.
comment, if you can put it up, I think that I'll have a better chance
What do you
to be
call that
understood.
thing? That's a special tetrahedron? What is that?
It's a
Just put it
space
up.
between four
It's what?
spheres. It's a space that is in between four spheres that are tangent in one point.
Okay. All right, good. I want to be, and I'm going to about to share that, but when I do, Manu, I'm going to share something else first. I'm going to share, and maybe it's obvious to everybody else, but I feel like that I'm finally, for the first time, really understanding some stuff. Here are 8 1/8 octahedra that you were explaining, Manu. And here are those 90-degree angles inside there. So basically I take a pyramid, which is half an octahedron, and divide it into 4 parts, making sure I maintain that right angle in the middle of it. So each one of these weird tetrahedra, irregular tetrahedra, because they're at 90 degrees on one side, there's a fourth of an octahedron, a fourth of a pyramid, or a 1/8 octahedron. So that's the first thing. I just wanted to share that. And then, oops, no, I don't need to do that. And
But just stay there, Steve. Just stay there on that thing.
okay.
And I'll explain how to change. Do you understand that the only way that they could appear like that is for the folding to appear and that they are hidden? Those that are visible? You could not see it from outside.
Yeah, you can't see it from outside.
Those 4 are inside.
Yeah.
They are covered. That's what I call covered.
Okay.
The
Covert.
4 tetrahedra, when I expanded, the 4 tetrahedra, you saw them clearly. They are overt.
Yeah.
Overt means seen.
These 4 tetrahedra are overt.
I put a definition in the chat.
And you put a definition in the chat. Do you want to read it?
Covert and overt.
Oh, I see.
Overt is open to view. Covert
Yeah.
is hidden.
Yeah, covert. Yeah.
Okay, so those are the words that I use. And I say that when you are dividing the octahedron, which Steve has done there, you divide them, the right angle tetrahedra are hidden.
Right.
And obviously, if the octahedron is implied is hidden, then they are hidden.
Yeah.
Do I have a chance? Does it add a little bit to my grade now?
You get a good grade anyway, Manu, even if I
Okay,
don't, even
but
if I don't understand what you're saying.
Does it improve? Okay, so that is it. So Steve, thank you. That has, I hope, you know, explain what I said by hidden. But
Yeah.
put my stuff in there. What I put in there. The snapshot.
I'm bringing it up here.
In the
Yeah.
It's
space,
loading in. Go ahead,
in
Fred.
in the space that's in the middle there between those spheres.
Okay.
Okay.
All right. Let me posit what I've expanded of Berkey first. Berkey say unity is plural at the minimum of 2. Meaning at the minimum of 2 tetrahedra, like this, the one that Steve was showing. 2 tetrahedra that form this. This is unity. Unity is minimum, is plural at the minimum of 2. This is what I define. A system is plural at the minimum of 3. Let me repeat it. A system is plural at the minimum of 3. A bow tie is a system. You have 2 wings, and then you have the axis, or you have the 0 point. A bow tie is a system. And the definition of system is something that is can organize in such a way that you can define the polarity. That is, you can define the way in and the way out. That's the system.
Boy, I wish Richard were here because
Okay.
I think that's profound for Richard. I'm going to say, Richard, because I get your conversation that this is a structure. This graphic is a
Okay.
structure because it's
Yeah, I'm
two-dimensional.
through. Yeah.
What?
I want to continue that. I don't even want to put dimension. I just want to put it in a street language that somebody can understand. A structure is plural at a minimum of 4. Because a structure defines the volume. A structure, you can say, for example, if you take me, Manu, as a structure, you have my skeleton and my skin. That's my polyhedron, but you have the content of me. Whatever that is inside me, that can be measured. I can say I weigh 180 pounds. I am a structure. So a structure is plural at a minimum of 4. Now come back to what I put there and then I'll explain what I wanted there. Actually, I had this when I was sleeping tonight, and then I just noted it down and then I finished now. That's what I was doing when we were starting this. Can you put that?
Put what? That picture back up?
The snapshot, yes.
Okay, I'll do that. And then you can share your thing in a minute, Fred, if that's okay. I'm going to say that what is the difference between a structure and a system, Manu?
A structure is a subsystem, is a unit of energy. Let's just put it this way. A structure is a unit of energy.
Is a triangle a structure?
If you're talking about the plane, if you represent, but it's not in 3-dimensional or 4-dimensional, a triangle is not a structure.
Okay, good. All right, I'm showing this picture again.
Okay. Now, so I've defined my 3 things in terms of unity, system, that's polarity of a unity, and then structure, that is being inside and having, let's say, a house where you can measure something. Now, let me put this together. If you see, I took 3 circles of different dimensions: smaller, medium, and wider. And then I drew them in such a way that they are tangent, as Fred says. If you take that triangle that is in the middle there, where there is a point in the middle, you see that one? The black in black, the one in blue.
In black.
Actually, it is on my stuff, is it? Yes, it's in black. You know, that is a structure, because you take the middle point that is actually in the dimension inside, in the third dimension, it is a tetrahedron. It is a structure. Now, look at the points of tangency of the circles. Just draw lines. Don't ask me why I drew it, but I draw line there so that I have an arc, and then the volume within the arc.
Right.
And then look at the points between the triangle that is tangent inside and those. There's a space there now that I colored yellow. Do you see those?
Yeah.
Yes.
Yeah.
That space there, mathematically, you can calculate them using ratios of structures, that you can fill it by deriving many. It is a solution to a polynomial problem. It is what you call an irrational number, but that is convergent. You can have a series of rational numbers that converge into it. That is a phi. Mathematically, it is demonstrable. Fred can do it. That space there, that is I'll call it triangoids, because it is things like this. Now, the space that it is in red, you cannot calculate it when you are in the system. If you are in that triangle in the middle there, you cannot calculate it. That space, in order to calculate it, you have to get out of your universe into one of the circles that are neighboring the next universe in order to be able to calculate it. And they cannot calculate it either in their structures. So that space there is transcendental to my structure. And you see that that arc, that is the arc of a circle there, that is filled, is calculated using a pi. It is transcendental. It is, to me, is hyperbolic from me, from my being inside in there. It is hyperbolic, it's going somewhere else. I don't know how to do it. The other one, you know that you have two types of hyperbola. You have this one. I'm just trying, that one there. Let me put it on the paper. If I'm here, you have an hyperbola like that, and another one like this. You see this one? If I'm here, if this is me here, you have an hyperbola like that, and another one like that. This one, I can't do anything about it. It's interdict. I cannot calculate it. This guy.
Hold it a little closer, Manu, because it's not there. Okay. What you have them both marked X. Mark it X1, X2, please.
No, I bar this one. I say 0 for me. I cannot calculate it. It is some infinite that I cannot reach. This one is some infinite too, but I can reach progressively. This one.
Okay. And please hold it up. Please hold it up so I can see it. A little higher. A little closer. Zonk. Zonk, I got it.
Technically not hyperbola. So,
I got it, Manu. Thank you.
Okay. If you
technically what, friend?
They should not share common X or common Y.
No, I'm not. I did not call them X. I'm saying I'm here. Just show it, Steve.
Yeah, I know you did not.
Yeah,
call
but
it,
you did
uh,
use two X's, Manu, and that was a
No,
little bit.
I was just bad. No. It's just unfortunate
I know
that I
you
use
don't.
it. Yeah.
Yeah, it is unfortunate. So what I'm going to do is I'm going to relabel it for you when we get it up here. Hang on a second.
Yes.
There we go. All right, I'm going to share it now. Oh, here we go. Okay. I should have saved it down and opened it up
Okay.
again. It would be a little
Right.
bit better.
Now,
'Cause I'm-
you see the black one.
no,
The
they're
thing
both
that's
black.
like the eight symbol. Yeah.
What?
That is like the AIDS symbol. You know the AIDS.
I don't know the 8. The X?
Okay,
I see an
on the
X.
black one and on the first X they call say me. Say me, M-E.
Okay, on this one here, I
Yeah,
say me.
yeah, yeah, me. That's
Me.
Manu. Yes.
Okay. You got me there. Do I have that right?
Okay. So let me talk in relationship to that me. If that is me, I will say that any point that is on the lower curve there, I can approach it with triangles like this in
So
such a way that I reach
the
it.
point that is on the lower curve, are you referring to this guy
No,
here?
no. That's not the curve.
You're
This one,
referring to
yes.
this guy here?
Yeah.
Okay.
I can build a polynomial series of rational numbers which are represented and that with triangles like this. I can do integration of triangles like this in such a way that I converge toward that point.
Okay.
Does everybody see that?
And this X over here was a mistake, right?
Yes, I was just saying that I cannot do anything with that. It's infinite to me. It cannot converge. It's a concept that is outside of my rationality. It's outside of it. Therefore, in order for me to account for it, I have to have a help from outside of my system. That's called transcendence.
Okay.
That's why they call pi a transcendental number. It cannot be a solution of a polynomial equation. Pi is not a solution like x cubed plus x squared plus whatever equals 0. Pi doesn't do that. Phi is.
Yeah. And so which one of these is pi? Both of these curves are pi, right, Manu?
Come, get to my stuff now. Get back to what I explained. Because all of this was trying to explain the first snapshot that you have, the one that was colorful, clear. There. You have a pi, you have the phi, and then you have the structure. In the middle is a tetrahedron. I hope everybody can see that.
Mhm.
Where's me?
Now, yeah.
Where's me? Where's the me? Is that the dot?
Now, the me was only in relation to the two. Now, the me is, yes, somewhere in there. The
Anywhere
me
in the
is,
gray, anywhere inside the triangle.
yes, anywhere inside the tetrahedron. It can be inside. Okay. Now,
Okay, so these are not circles, these are spheres.
yes.
And that's not a triangle, it's a tetrahedron.
Yeah. Now, you take it there. If you take the yellow part, does everybody see that?
Which is the phi part.
Exact. That is the phi.
Because we don't see yellow. I'm not seeing yellow on my screen, Manu, so I apologize.
You don't see, okay, yes, where I put phi. There are the three edges
There
of
are
the
three
interior.
phis. There are three
Yes.
phis. Right.
Yes. So that is the phi. We can calculate the phi.
Right.
How do you calculate it?
By series. So it's a polynomial equation. We saw it in a
Oh, this is
yes.
2D, right? This is three circles tangent.
Yes, this is straight circle representing sphere. I just did it on the
So-
paper today.
So pi is pi what? Is a surface?
Phi is the number
I know,
1.642. Yes.
I know. But on this sketch of yours, phi
It is
one,
just, yeah, it's just surface, the yellow surface, the golden one. You see it in three parts.
and pi is the pink one.
Yes, pi is the pink one.
Okay.
You see that pi is outside of my system.
What the unit
Unit of what?
of surface? Because
There's
pi,
no unit.
yeah,
We're
but
talking
yeah, but-
topologically here.
yeah, but
Yes.
it's pi what?
Pi is 3.14. Is the number.
Yeah, 3.14 what?
Energy.
Units of-
I don't know.
Of
Maybe
whatever it is. Pi
Yes.
In this special case, we're talking about pi
No,
units of
this is just
pi-
a representation to
it's not.
express
It's
what.
a measure. It's not a representation. It's a measure. You're
Okay,
measuring.
tell me what it is.
You're measuring a surface, and you say the surface is pi, but it has to be pi number of units. What is?
No,
the
I
unit?
didn't say that. I didn't say
What?
that.
So it's pi what?
I say to do any measure, that's what you call the macro. To do anything there, it has to be something outside of your system. It's macro. As well as in that dot that is in the middle.
So what is the pink exactly?
The pink was just a representation of an area of where the structure
So-
is fair to show
So it's an area
pi,
between.
that pi is required.
It's the area defined by the two tangency points with the other two circles and the chord.
Except this is
the chord
topology.
The chord between on the one circle between the two tangent points and the arc. Yes.
Except that this is a topological metaphor. It is not meant to represent any specific structure that can be measured in any specific way. This is a topological description.
Yeah, okay. So what is pi? Where does that come from? If it's not a measure, what is it?
That pi intervenes in the estimation of something that is radiant.
Yeah,
That
it's
is going.
percentage.
Yes, it is
It's
going anywhere.
Okay,
So
how
there
do
is
you
a
come
constant.
Okay, fine. How do you get to pi?
Okay,
point?
what is Steve?
What
What is
Hold it.
the tetrahedron?
Manu,
What
allow
makes you so
Fred to
sure
ask his
that
question.
this area in pink is pi? Because you say it's topology, or Stephen says topology, so you cannot count and measure. Fine. So what is pi if you don't measure it for something?
I'm saying that area there, in order to have any idea of it, you need pi. You need pi. And you cannot make pi. I can make phi. I cannot make pi. Pi is transcendental.
Pi is 3.1416, which is a percentage of something.
It's a ratio. It's a
ratio
ratio
of
between
something.
between the diameter and the circumference.
But it is, do you understand that it is transcendental?
Yes, but that doesn't help us to
Okay.
understand.
Do you understand
Okay.
that everything that I measure is because there are ratios, is rational. If something is irrational, I cannot measure it.
Yes, you can measure it. Yes, you can.
No.
You can measure
Can I
it
say
by.
something? Can I say something?
Yes.
In order to measure anything, I need as a base a system that is rational. I can make ratios of something. That is, I can compare to something. That's the only way you measure.
Yes.
This is the principle.
Yes.
I can compare to something.
Yes, but why are we talking about something?
No, hold on. Okay, I'll
What
let
is
you
pi
speak.
in that case? Because you say it's a pink. Okay, please define the pink. You say it's pi. And I say, what is pi in that case? And you say, because it's pink.
Fred, let's say that is a circle and that is an arc. And that the area in yellow, in order to calculate it, I need that base that is there. You see this, you see the straight line base of it?
You're talking about one of the three straight lines that form that triangle.
No, the external triangle.
Oh, the external triangle. Okay.
Yes. Because they asked me a question, what do I need to calculate it? I say, in order to calculate any of the pink, say, areas, I need that
Triangle.
yes. No, I need the base, and I need the number pi. I cannot calculate it without putting pi in. But when you take the yellow one, I don't need pi. I just need ratios. I can integrate it. That is, I can calculate, I can put triangles of different sizes, different shapes to fill that phi. It requires an infinite, a very high number of triangles. I can do it. I cannot do it outside there. I can't. If I'm in the point that is in the middle of the internal, is that where I'm measuring from? Impossible. If you can do that, you tell me. Because whatever arc that you are going to do there is going to be explosive. It's going to go, it's not going to be limited. You can't measure it. You need a help. Fred, do you understand that when you say the ratio of a sphere to the diameter, that is constant, that it didn't come from inside the sphere? It came from the neighboring sphere, because that's the one that is seeing the sphere. You don't see any sphere. You can't measure it. You don't see any sphere, I repeat. You are in universe. So you need a transcendental number. It's like the base of the calculation, that is E, 1.41, whatever. It needs to be given to us. We couldn't get it on our own. It is revealed to us. We can't make it. The other numbers we can make, that is revealed. If I'm mysticist, that's where mysticism can come in. It comes from that, it is revealed to me from outside. It's not part of my system. So my point is, yeah?
As a point of information before we continue, phi is yellow, right?
Yes.
Okay,
Yes.
so I'm going to leave that in there because my diagram does not show yellow. So I'm going to leave it in there, and that way, whoops, what the hell happened? I'm going to leave it in there because those who are listening to this recording are not going to see yellow unless they do. So that's the first thing. And you're saying that this circle, I can't see it's a circle because it's outside my system. I just have a boundary.
Yes.
Is that what you're saying?
Yes. It's
Okay.
part of a boundary. Any boundary has a covered pi that is a phi, and an uncovered pi that is a pi. Any boundary that you define, there is part. If you have the boundary wall of your house,
Yeah.
a face belongs to you, the other face belongs to your neighbor. I can do a lot of drawing, a lot of things on my face of a wall. My neighbor will never see. He will never complain.
And
The
you're
day
saying,
that I poke,
and you're
the
saying
day
that
that I'm saying, Steve, we are neighbors. You have your house, I have my house. And then we have a neighboring wall that is between us.
right.
On my side, I can draw whatever. I can even make shit there, no problem. As long as it doesn't smell, you don't complain.
Yeah.
It's not your problem. You don't see your neighbor. The day that I poke a hole in the wall, in our common wall, boundary wall, in such a way that you can perceive it, it becomes a problem, true or false?
Okay. But every boundary is a pi.
The macro side of a boundary
Is
is a
pi.
pi. Yes.
Okay. Now
The micro, the inside part of it, the concave part of it is a phi.
Okay, I'm going to put down the word concave here as well.
Mhm.
And then Fred, you've been asking some good questions. I'm not sure that your questions have been heard or answered. Do you want to do what you can to restate this?
No,
Restate your,
I think I understand what Manu wants to say. He wants to say that in order to calculate the pink part, you need to use pi somehow, one way or another.
yeah.
And in order to calculate the yellow part, you need phi, one way or another. The corollary to that is pi is included in the pink and phi is inherent also included in the yellow. But the annotation on the diagram, that's what it means. But when you read it without an explanation, it means that, I mean, it could mean that the pi is the pink surface has a value of pi, whereas the yellow surface has a value of phi. And my question was related to that. How do you get to there? And obviously, if it's just that you need pi or you need phi to calculate each surface respectively, then of course it's not how you get there. So my question was to understand why is it pi and phi? Why are pi and phi annotating this diagram? And I think I've got the answer.
Good.
So
So let
thank
me
you.
ask you, thank you. And so that's resolved. Now, I may have misplaced. Is the concave the yellow?
Concave
think
and concave and convex is going to be relative to your position.
Exactly. And I'm inside the,
Exactly.
and I'm going to be inside the system, right? So am
Yeah.
I experiencing is the yellow concave or is the yellow convex?
The yellow is concave.
Okay, and pi is convex.
Yes. And it's important to note that the yellow and the pink form the boundary. So the other side is the parallel universe, is another universe, which I don't know, but a lot of people have hypothesized on it. And it's important, Fred. Yes, I understand where you came from. I just did it here. I didn't do, I didn't put a lot of thought in it, but it was just to mend what I was thinking. Because I say I had a hunch when I was sleeping tonight.
And the pi, the pink, and the phi, the yellow, are the boundaries for the observer, for the observer who's inside the structure, the system.
Yes, yes.
Oh, shit.
And then you can also put that, Steve, in your language into the tantamountly something. You know, your spheres of how do you call them?
Spheres of irrelevancy, the circles of irrelevancy.
Relevancy, yes, yes. The phi is very related to the tantamountly. I don't know what were tantalizingly.
Tantalizingly.
That, yes, that Bucky uses.
Okay, and I can bring up the circles of irrelevancy one more time because this is not the best chart. I think that I think I'm not showing it either because I think I'm on a specific thing. So now here we go. Oops, there we go. So now here's the one rendering of the circles of irrelevancy, and there's the twilight zone, which is almost relevant or tantalizingly almost relevant. And this is the twilight zone. This is a different one. He uses twilight zone in one metaphor, and he uses tantalizingly irrelevant in the other. This is twilight zone of almost relevant.
That is a phi. In my opinion, is a phi. That's my point.
And the pi is the blue stuff inside.
You have conceptually, you can build it. Yes.
Yeah, and here's your concave and convex.
Yes.
Here's gravity and radiation.
Yes. And it came from the hierarchy that I say in the beginning: unity, system, structure, and hyperstructure. Unity is plural at minimum of 2. A system is plural at minimum of 3. And the definition of a system is putting things together in such a way that you can see an input and an output. A triangle is a system. To say, for example, the box, the feedback loop, and in-out is a system. A structure is plural at minimum of 4. That is, you can actually make it a tetrahedron. You can fold it into a unit of measure of energy. And hyperstructure go further than that. You can see this thing also in terms of, remember when we talk about stability, there are degrees of stability. If you take the most stable is represented, when you do your representation, the most stable is the biggest pendulum, right? I'll say again, right? The biggest pendulum that does this. That is, if you hit it with a lot of energy, it will swing one side, but it will come back, gravitating towards the trough point. But a representation of it is a smaller in volume, is the most dense. Concept of unity is also that of volume and density. We should never talk of volume alone. We should always say a volume of this thing that we know that is of a given density. It is a unity. Volume, density.
Okay, and then you gave it, I think, Fred, you're giving a definition of in mathematics, a polynomial is a mathematical expression consisting of indeterminates, also called variables, and coefficients. And then I think your next entry was an example of a polynomial. Is that correct?
Yes, that's an example.
Okay, very cool.
You remember the way we calculated the golden ratio at one point, Steve?
Do I remember how we did that?
Yes. We say x equal x divided by x plus 1, I think so. I can't remember. That is a polynomial equation. Everything.
1/1 plus square root of 5.
Yeah.
Or minus square root of 5, let's say.
Yeah. Square root of 2, for example, is an irrational number, but is a solution of a polynomial equation. It is as irrational as pi, but you can never find pi as a solution of a polynomial equation. So the transcendental numbers are a subset of irrational numbers. Every transcendental number, pi, the number that you talk about, Steve, I think like Wilson, whatever constant and things like that, they are transcendental because they can be found within your rational structure. You cannot
Because they cannot be found?
You cannot use your rational structure to calculate them.
Yeah.
Rational means ratio.
Yes.
Means an irrational number, I put the definition in the chat, is a number that you cannot express by a ratio of integers.
Yes.
Integers are numbers that do not have decimals, like 1, 2, 3, 4.
Right.
These are
Thank you.
integers.
But the link here, Fred, is that when we talk about integers, we have to talk about unit of energy. That's the link between math and physics.
Integers are what made Pythagoras become crazy.
Yeah. Is a unit, an integer is a unit of energy. An integer is the multiplier of a tetrahedron.
Do you want to explain why Pythagoras went crazy, Fred? What's the story behind that?
The story behind that is that Pythagoras was sort of an idealist, and it was a sect actually, the Pythagorean sect. And they wanted to describe the universe as integers. Everything had to be integers, and they had to find formulas to express everything. So they discovered pi, and the whole world crashed on them because pi was not an integer. And they could not express pi as a ratio of integer, and they proved that they could not. They even, the historians are divided on that, but they even made some of the disciples, some of the students disappear when they came up with questions about pi. They made the guys physically disappear because the guy was denying them their ideal vision.
I love it. Thank you for sharing that. As I'm listening to this, I keep coming back to my recently discovered animation of pi, which makes me understand what it is, because, and I'm not going to play the whole animation. I've done this PDF file and broken out some of the key steps in the animation, but it starts out almost looking like a phi, but it caves back in on itself and then starts to form the flower. And, oh, this should be, oh, this is exactly right. This is a completion of the circle. And just when it starts to connect itself and become rational, it misses itself by a hair. And when it misses itself by a hair, it starts tracing itself around until it just goes apeshit crazy. It never is rational. It continues to stay irrational. And this animation really helped me understand transcendental numbers, Manu.
And let me say another thing. Pi is as a consequence of the pulsatory nature of universes.
Of the processionary nature?
Pulsative. Universe is pulsative.
Oh, pulsating.
Yes.
Of the pulsating nature, the jitterbug nature of the universe.
Yes. And that is infinite.
Yeah.
That's why it's transcendence is a principle. Okay,
Manu,
let's not go there.
Manu. Let us have our moments of epiphany here. Don't just keep rolling. Pause for a moment. Because when you said universe is infinite, my heart started to flutter. I got this transcendental nature of universe. And I got so very excited. I've almost got tears in my eyes. So thank you for that epiphanal moment. If that's a word, thank you for it.
Wait a second.
Okay, Fred's gonna screw me up now. I'm gonna come down in tears. Okay, Fred, I've got my tissue ready.
I'm taking you back to the origins. Okay, let's say universe is finite on the out. How about on the in? Because when you look at pi, and with this infinite series of decimals that you can never end because it's transcendental, what happens when you reach Planck length?
Yeah.
That's all I
It
want.
it is still in there.
Yeah.
It goes to the mind.
I don't want to argue that. Just
Yeah, it's a good question though, and this is what Donald Hoffman argues, that space disintegrates at 10 to the minus 33, I think, and time disintegrates at 10 to the minus 43 or something. Planck time and Planck space, and so
Planck time is you know what Planck time is? I put in the chat. Planck time is a derived unit. It's how long it takes light to travel 1 unit of Planck length.
Planck, yeah. I saw that, and that's yeah. I saw that, and that's totally because when I said the 10 to the minus 33, I was only doing space. I wasn't doing time. And Donald Hoffman says it disintegrates to 10 to the minus 43. I may have the numbers wrong, and you may have them right in here, Fred. I don't know, but that's cool. It's cool
But
that
you know,
the reality I perceive disappears. That's this. Go ahead,
Yeah.
Manu.
Do you know why we have problems?
Do I what? Oh, and let me
You
say this. Let me say this just for the record. Not only does it disappear at 10 to the minus 43, it disappears at 10 to the plus 43.
Yeah.
In other words, it has a bottom limit and a top limit, and then our physical universe breaks down completely and something else exists. Our
Yeah.
universe is contained within whatever else is holding that blank space.
Yeah.
Go ahead.
I was saying that we are in difficulty with because we constantly violate one principle. The principle is that of a duality of space boundary. So we always forget that once we've set a boundary somewhere, or discover a boundary, what we know is within the limit of that boundary. If we start questioning, we have to question the boundary and change it. And it means that the paradigm that we have developed for that level will probably dissolve. Some will stand, but some will dissolve because they were just specific cases. So let's always have it in mind. The fundamental principle of duality. To anything that you do, because we don't see. And that fundamental principle of duality stems from the fact that we are in a system and we cannot see the whole system. That's why there is a boundary. It is topological, it is fundamental.
And here's that boundary, Manu. This is from Lafert's book, Cosmometry. And this is the calculation of phi. And that's where the phi boundary occurs right there. That's where the torus, that's where the torus is. Anything outside that's beyond our experience completely.
Is a pi. For us
This
to
is a
understand
pi. Out here is a pi.
Yeah. Yes.
Oh, very cool.
Because the only thing that we can represent with it is to put another sphere.
Yeah, there it is.
That's the only way. If we put enough sphere around it, we can have an idea what it is.
Oh, I really like that. Out here is a pi. Inside here is a phi. Wonderful.
I invite everybody to go and study the hierarchy of numbers. Just numbers without anything. There are so many representations on the net that gives you insight into what are we talking about here. Just taking numbers and say the why numbers. Why is this? Why is it like that? Just go. It is given. Because we went to school, they teach us 1, 2, 3, and then they introduce and the real numbers. We tend to forget that pi is actually a real number. So
it's transcendent, it's irrational, but it's real.
Yes. And because it's like this, and because of principle of duality, there is the imaginary axis that is perpendicular to the real axis. That is infinite. That one, imaginary. That's why you note a number by Euler's relationship. When Euler says exponential of I multiplied by pi plus 1 equal a sphere. What does it mean?
I don't know.
But that's what we live with. It's a bow tie.
Yeah.
What you see is 1. What you don't see is -1.
Yeah.
And that put together give you the poles. That is the 0, the cipher.
Cool.
The cipher was invented. The cipher is not linear like this. We tend to see the cipher like something that is part of the real number. It's not. It is, what we see is the representation of another axis that comes and hit it at 90 degrees. Phi is not a real number. We assume that is part of it. We call it absorbent element. Because if you take any operator, whether additive or multiplicative, if you add anything to the cipher, you have that same thing. If you multiply anything by the cipher, that is, if you compose, you allow the R cipher to come, to multiply is to come perpendicular. We have to get that into our mind. To multiply is to divide. You divide to multiply. This is 1. This is divide. This is 1. This is divided. When I do this, I start 1, 2, 3, 4, 5.
Cool.
And the cipher is this line here, where the 2 meet, which I call 0. But it was just invented by Arabs to make sense of the numbers that we were seeing. So look at the numbers. I'm telling you, it is beautiful. It is something. You don't need 1 million equations. Just look at this table here. This is not difficult. And start making things about those boundaries that they put there.
You're talking about Fred's diagram that's now showing on the screen?
That's one. Yeah, that's one of the things that you see.
Yeah.
Yes. There are many, 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 many. Really. And link it, try to link it to units and the thing that we're studying in physics.
Right on.
And then you start having, because we've used this at school. Everybody has used these kind of things. We've all done square roots. We've all calculated the areas of circles. We've all done complex numbers that represent with one number, this face and that face.
I don't
Sine
think we've
and
all
cosine.
done complex numbers. You may have done complex
You don't
numbers.
sine and cosine. What is it?
I never did cosine and sine.
You've not done complex numbers?
I've never worked with, I quit,
Okay.
not because I wanted to, but I just didn't know there was anything out there. I quit it.
It's very easy to tell you what a complex number is.
I think I have a definition, but please tell me.
Complex number is I. It's a name, I. And I is equal to the square root of -1.
Okay, cool.
Okay? That means if you multiply I by I square equals -1.
Mm-hmm.
Okay? And there's a lot of, a whole domain of mathematics that derives from that. You would not have quantum mechanics, you would not have
Oh, yeah.
cell phone, you would not have any electronics without complex numbers.
Yeah, I've watched a video from Vertasium on the development of complex numbers and how they were being used practically all the time to solve problems, and nobody was aware they were using them. And finally, somebody explained what a complex number was. There's quite a story about the history of the complex numbers. It's pretty cool.
They're
Evidently,
also called imaginary numbers.
imaginary numbers, right? I. That's why it gets the I.
Do you know what you call imaginary numbers, Steve? Let's say I'm looking at you now, each of you. I see Anne's face.
You see what?
Anne's face. That's what I see. I can say yes. Oh, Liz. It's Liz. Anne is not yet. I see
Okay,
Liz's
good.
face. Yes. I can say Liz's face is over.
If you see that space,
yes.
This is the essence of imaginary numbers, is when you see.
Okay. So, but I cannot see Liz's back. But I can imagine that the back will be some kind of symmetrical or something. You know, the back is going to be colored with hair black, but it's going to be a mirror image or something like that of Liz's face. So I imagine it. That's why they chose the operator I. I imagine it. It came from imagination. That it is going to be like this. Then I put a coefficient onto it to say, Liz's back is I, her face.
Cool.
The projection of her face. And that's why to have Lee's complete picture, I say Lee is equal this over letter C plus what I imagine by a coefficient, which is something that is real, letter C. And that's how the complex numbers, the notification came by. And you say you didn't do it, you did it, Steve. Did you do time?
Actually, complex numbers were invented. I forgot the name of the mathematician that did that, but they had a challenge between mathematicians of who would be able
Yeah.
to come up with a solution to the third degree polynomial.
Yeah.
And one of them came up with I, that is, he had to invent the concept of square root of -1 in order to be able to come up with a formula
Here it is, Toscano.
solve the third degree polynomial. Third degree means x to the power 3.
Mm.
And
I
I wanted to add, if you like precession and 90-degree stuff, looking into complex numbers will give you a lot of insights into 90-degree stuff.
Yeah.
Exactly.
And let me tell you guys, this video is fantastic because it talks about the two dudes, this idea of Cardano and
Oh,
Bombelli.
Cardano. That's it. Cardano.
Yeah,
But Steve,
1579,
Cardano
50.
is the inventor also of the carbon
Steve.
joint. Of course.
Ah,
all come from here. This is the first dimension. Let's just say here, this is the real. You see this tetrahedron that I'm pointing to you. I can see when I look at it, I can see this face with all its reliefs.
right.
That is it. The one that is behind there, that one, the white one,
Yeah,
is the complex part of it. I don't see it.
yeah. And that video explains this very well, and does
Yeah.
it explains it in 2 dimensions, and it's really
Yeah.
profound.
But I was saying that, did you do time in primary school? Time.
Did I do time? Yeah,
Yeah.
they put me in primary school for till I was
Yeah, but
till I
they
went
do.
into junior high.
They add you. They ask
You
you
did your
to add.
time.
They add you. They add you. They ask you to add time now. If I say 15 hours plus
Yeah.
10 hours,
Yeah.
will you say 25 hours?
No, we measure time in terms of 60 minutes per hour.
Yes. So 15 hours plus I say 16 plus 8 plus 9 hours is 2 or 1. Does it make sense to you?
No, but that's okay. It doesn't frustrate me all because I know Gödel's
The
theorem.
the period is 24 hours. That's the convention.
Uh-huh.
If I take 15
Yeah.
and I add 8 to,
Yeah.
and I add 9 to,
Yeah.
no,
24.
I add 10 to, I have 25.
That's right. Suddenly I'm
1.
1 over. Yeah.
Yeah, it's 1. And then further, when you went into secondary school, they taught you what you call modulo. A module. Your fractals are modulo, Steve.
Yeah. I
Your
wish they would have
fractal-
taught me about fractals.
So never be afraid. Never be
Your
afraid
Mandelbrot set would
yeah.
not exist without imaginary numbers.
Yeah.
What without an imaginary?
The Mandelbrot set,
Mandelbrot without imaginary zones. Absolutely correct. And I'm in love with Mandelbrot and Julian set. These things blow my mind.
all this family of fractals would not exist without
Absolutely
without
right.
imaginary numbers.
And it's the
But remember that we first experience most of the time. We need a primer of something. We experience something that is weird.
Yeah.
And then that kicks in the chemicals of our imagination.
Yeah.
And we start looking for explanation, that is for principles that will make it seem something that we can accept.
Yeah. This is why the video, the animation of pi blew my mind, because I got how it almost connects, almost becomes rational, but does not quite. And as a result, it just keeps going on and keeps going on. That blew me away. Okay, it's
It was that close.
that close. That close. Okay, it's 12:53. Luckily, there's only three of us here, and hopefully we won't go on for, oh, there's four of us here. Hopefully we won't go on. I was thinking my host and three people. Let's go ahead and have our takeaways now. Fred, how are you feeling and what do you take? Are you ready for takeaways or do you want me to come back to you?
I'm good.
Okay, good. How do you feel and what are your takeaways today?
Thank you. I was energized when I came in. I'm even more energized now. So that's how I feel. My takeaway is going to be that when one of the participants is pinned, like I have Manu pinned there, it's very easy to count only 3 participants when there's 4. That's my takeaway.
Okay.
So Lee, Madam Lee, how are you feeling and what is your takeaway for today?
Unmute.
You unmute, we cannot hear you.
I am unmuted. Wow. I got maybe a tenth of that. And the rest went over my head, and I'm still pondering, wondering what can I do at learning all of catching up to you guys. That's going to be a hard thing to do. But this is fascinating. My takeaway from this is that I see art in it. And I think I've said this before. I see art in everything that you're talking about. And it explains it when I see that art. I'm trying to remember the statement that Manu made. That was pertaining to that. And it's gone from my mind, but I love that picture. And I saw the yellow in that picture. I saw the pink and I saw the square way over what Manu drew. And I understand that. The emptiness has a calculation now, which is nice to know. I have much to learn. That is my takeaway. Thank you.
Pass it on.
Fred,
Manu.
Manu, how do you feel and what are your takeaways?
I feel as excited as Fred and you, Lee. And what I would say is that never be afraid. We like to use pompous words. And I try to suppress myself from time to time to get back to basics. That's why I always try to get back to basic. To get back to basic is like looking for your north star.
Mm-hmm.
Looking for your anchor. Where is it?
Mm-hmm.
And to me, that anchor is 3 things. It is unity is plural at the minimum of 2 tetrahedra that come at 90 degrees of each other. So that is unity is plural at the minimum of precession. Secondly, is that a system is plural at a minimum of 3. To do anything, we need a system that is a conduit of energy. Because remember, energy is everywhere. So, because of the first one, unity is plural minimum of 2, boundary and space. Now I need a system. So the lines of flow. That is, a system is plural minimum of 2. Now a structure is plural at a minimum of 4. Because remember, a structure is meant to create a fractal of a stable system. Is meant to be made to be stable in such a way that you can see something that makes sense to you. And what makes sense to you is a unit of energy. And the typical of it is a tetrahedron. And the tetrahedron has 4 vertices. So a structure is plural at a minimum of 4. Then we want to go further than structure. See that we want to go deeper, but we divide more. An hyperstructure is plural at the minimum of many. And one being the truncated octahedron that Steve was talking about. You remember that? And then for it to fit, if you remember when we read, he said it doesn't fit neatly like a tetrahedron. You need to twist it 60 degrees. And when you twist 60 degrees, what are you creating? You are creating triangles. And I twist 60 degrees, I'm creating tetrahedra. So it becomes now a composite of cubes and tetrahedron. That's what they call the cube octahedron field space. And that is the minimum. That's what I take away from this. Explained like this, I think, can be understood by everybody. I don't need to be a nerd. I don't need to calculate things. But I just need to tell myself a story that relates me to what we're talking about in a way that is viable, in a way that is stable. It is a story. We are storytellers. And that's my biggest takeaway. We tell stories. Okay. So otherwise,
if I may interrupt, I
Thank you, Manu.
remember seeing a picture that I don't believe everyone can see it. I look at trees and I see the different colors, but I see diagrams within that tree. And there's one outside the window that I look at every day. That's a huge heart in those leaves. But I don't think anyone else has ever seen it. And that's where the art comes in. And I can see, probably if I look long enough, tetrahedrons within that tree. Go ahead.
yes. So Lee, just taking you on what you see. Remember that red, for example, if I see a tree, and if it's spring, it blossoms, right?
Yeah.
I'm taking away the right here, it blossoms. So when it blossoms, say for example, there are red petals. That red is structured. It is stable. You can see it clearly for quite a while. And that is in a form for it to be structured, and that is the principle. Anything that is structured is made of a combination of tetrahedra and octahedra, or parts, any combination of the 1/8 part of the octahedra that Steve talked about.
Mm-hmm.
That's what you call rational numbers.
Mm-hmm.
It is made of those. If you get that, you understand the rational numbers in a way that is useful for you to use. That anything that you can, and that's what the painter does. It takes those things and mix them. That's what a musician does. It squeezes notes, and sometimes it becomes creative, like B.B. King, who came up with his own way of playing music, and that became mainstream. That's how we can create, by recombining, and the way that we recombine things is infinite, is inventiveness. So finite energy, but because of a cycle, we can divide it and recombine it into an infinite ways possible. And that's why the symbol for infinity is this thing that looks like this. Is the sine and the cosine. That's one cycle. Did you see that, Steve?
Yes.
The sine and the cosine. 360 degrees, 360 degrees. The other way, this way is like this, like that, and that way is like that. Plus, minus, plus, minus. If you look at that, that's the way. And the two are pulsative, they are alternative. They don't come at the same time. I have this. If you look, the first quarter comes like this, goes like that, and comes that way. It's energy flow. Two events cannot take place at the same time. Otherwise, another event that is called collision. Or you ride, like I'm riding on a plane, me and the plane becomes one thing. So by seeing this with metaphors like that, we understand it. And then we understand the imaginary numbers, cosine and sine. Precession, we understand it also that way. It's the composition, this one first and that one after. That's the best, that's the biggest thing I take away from all of these discussions. Thank you. Sorry to have taken all the time for me. Steve, you can find me. That's good. I'll pay.
I need lunch money this week, so thank you. Thank you for the
Over to you,
permission.
Steve. How do you feel? What do you take away?
Well, I'm going to feel good having lunch this week. Thanks for volunteering to pay a fine. First of all, I'm excited that we have a Picasso amongst us, Lee. Thank you for looking at a tree and seeing all sorts of weird stuff. Good for you. I'm also really I feel like I'm in good company, and I loved hearing the story. I didn't know Pythagoras was going to go crazy because he hated he just couldn't comprehend irrational numbers. There could be nothing irrational in the universe, and Pythagoras went apeshit. Luckily for me, I've seen the animation of pi, and I saw it before I had my life crisis, and so it resolved that quickly. I'm delighted. Um, I've never gotten the relationship between rational numbers and ratio and integers. Oh my gosh, that was good for me tonight. Um, and um, and I love the idea that pi is outside of phi, and that phi creates pi and phi together. There's a boundary there, and I love that. And Manu, your chart of the triangle inside of the spheres, well, it drove me crazy for a while because I couldn't see the yellow. But having resolved those issues, I'm grateful for all that. Um, and I really want to say that you guys probably, but as far as the history of irrational numbers, I put that Vertasium link in here. It's absolutely fantastic. Fred, you're right. There was a competition. One guy figured it out, and he held, because back in the day, if you were the smartest guy, you kept the job. And so he kept the secret. And then the story is he died with the secret. And if it weren't for the nephew, who was not under a blood oath not to reveal the secret, they would have had to been rediscovered again. But they discovered the writings. It's a great story. And thank you for reminding me of that. And I put the link in there. I love the fact that we are all storytellers. And that gives me confidence because irrational numbers are just a story. It's just a story. And I would feel obligated to learn about all this math and everything, and that I would not be able to sleep until I learned it. But Gödel's theory has saved me. Gödel's theorem. that math can't prove anything. There are limits to what math can prove. And so I can go to sleep at night and not feel destroyed about not knowing all this math. Although I respect you guys a lot, I'm okay, thanks to Gödel. He saved me. So those are my thoughts for tonight. And we'll probably next week, if everybody's okay, we'll start reading the last two paragraphs of what we just read tonight, because it leads into the next part once again. Fred, you sound like you look like you're bubbling over there. Do you have a
Yeah,
comment
well,
or something?
just go ahead, finish.
Okay, and so I think that's what we'll do next time. I'm all excited. We'll start on page 207, and I'm complete. So if there's any other comments,
Yes.
please.
And a structure is plural at a minimum of 12.
Oh shit. And Fred pointed up there that the minimum number of features in a system is 30 according to Bucky. So you're a bit short, Manu. Go ahead, Fred. What were you gonna?
I would like to thank you for volunteering for demonstrating the Gödel theorem for us next time.
Oh, yes.
Yeah. No, thank you.
I will
Prove
work
it.
that.
I have a good Vertasium video on Gödel's theorem, I do believe,
Well,
but I won't
Yeah,
do
but
it.
Veritas, I mean, he's not proving it. He's telling you somebody did.
That's right. That's exactly right. He's just a storyteller. He's just a storyteller, as we all are.
We are all storytellers. That's
And I'm
what we
so
do.
honored to be hanging out with you weirdos. Thank you very much.
The hero of 1,000. You remember the book?
Yeah, the hero of 1,000 journeys. It was Joseph
No,
Campbell.
the one that was written by
Joseph Campbell.
yes.
Yeah.
Of a figure, 1,000 figures or something. I have a book here.
Is hero of 1,000 journeys. I'm pretty sure the word is journeys.
Yeah,
All right.
something.
Thank you very much.
All right. Good
Bye-bye.
night, all.
thank you.
See you.
Fred, good night.
Good night.